Section: Introduction. In this section, we discuss the significant advancements in frontier AI systems over the past 5 years, which have evolved from simple text generation to independently conducting complex machine learning research projects. These advanced AIs have the potential to perform dangerous tasks, such as developing weapons and self-replicating without human oversight. Understanding these capabilities is crucial for establishing safety measures as AI systems grow more powerful. Many developers are now using specific AI capability metrics to guide their risk management strategies. We recognize that current benchmarks for assessing AI capabilities have notable limitations. They often focus on artificial tasks rather than those of real economic value, and they tend to favor tasks where AI struggles compared to humans, skewing performance comparisons. Additionally, benchmarks quickly reach a saturation point, making it difficult to compare models with vastly different abilities. To address this, we propose tracking AI progress through the Task Completion Time Horizon, which measures how long tasks can be completed by models at a certain success rate. Specifically, we define the X% time horizon as the duration of tasks that models can complete about X% of the time. We test this approach using 3 datasets that include a variety of tasks relevant to research and software engineering, totaling 170 tasks of differing difficulty. We estimate how long a knowledgeable human would take to complete these tasks and evaluate the performance of 13 frontier models from 2019 to 2025. By applying methods inspired by human psychometric studies, we determine the 50% time horizon, which has shown exponential growth from 2019 to 2025, doubling approximately every 7 months. Our findings indicate that this growth rate remains consistent across different task types. We also analyze the 80% time horizon and observe a similar trend, although these horizons are generally shorter. This progress seems to stem from improved logical reasoning, better tool usage, and increased reliability in task execution. However, we note that current AI systems struggle with less structured tasks, raising questions about the applicability of our findings to real-world scenarios. To further validate our results, we conduct 3 supplementary experiments. First, we replicate our methods on a dataset with human difficulty ratings and find that the exponential trend persists, albeit with a shorter doubling time. Second, we assess our tasks against various messiness factors and discover that models perform worse on messier tasks, yet performance trends remain consistent across different task complexities. Lastly, we evaluate AI performance on internal pull requests and find significant variations in completion times among different human groups. Our experiments suggest that while performance trends do not appear slower on more realistic tasks, we cannot rule out the possibility of slower trends in tasks necessary for automating software engineering jobs. We conclude by discussing the implications of our findings for forecasting AI capabilities, noting that if current trends continue, AI could reach a task completion time horizon of over 1 month by late 2028 to early 2031. However, we acknowledge that this projection is influenced by external validity concerns and potential changes in growth rates. Section Summary. In this section, we analyze the rapid advancements in frontier AI capabilities over the past 5 years, highlighting the need for robust benchmarks to inform safety measures. We propose a new methodology to track AI progress through task completion time horizons, revealing an exponential growth in AI performance, while also addressing limitations and external validity concerns related to the tasks used for evaluation. Section: Related Work. In this section, we discuss related work in evaluating AI capabilities. We note that the assessment of AI has progressed from simple benchmarks to more intricate evaluations that mimic agent-like behavior. Traditional benchmarks like GLUE, SuperGLUE, and MMLU have been useful for understanding language model performance, but they mainly focus on static knowledge rather than the dynamic problem-solving skills needed in real-world scenarios. We highlight newer benchmarks such as AgentBench, which tests agents in various environments like web browsing and gaming, and ML AgentBench, which is tailored for machine learning tasks. ToolBench evaluates how well AI can use tools, while ZeroBench focuses on reasoning through visual puzzles. Other important benchmarks include Gaia, which assesses reasoning across different modalities, and BigBench, which features a wide range of tasks requiring multi-step reasoning. We also recognize software engineering as a key area for evaluating AI. Benchmarks like HumanEval and MBPP present programming challenges of different complexities, while SWE-Bench and APPS test more advanced programming skills. We utilize SWE-Bench verified human time estimates for task completion in our research. RE-Bench, which we include in our dataset, assesses models on complex engineering tasks that may take hours for humans to complete, comparing AI performance to that of human engineers. While these benchmarks offer valuable insights, they often lack a unified metric for tracking progress and comparing models with different capabilities. Our time horizon approach aims to fill this gap by providing a continuous metric for measuring progress across various capability levels. We then turn to forecasting AI progress, noting that various methods have been used, often starting with the observation that the compute power for AI training has increased significantly over time. We mention that compute usage has been doubling approximately every 3.4 months from 2012 to 2018, and that this growth correlates with improved AI performance. Recent studies have also linked benchmark performance to factors like release dates and compute usage. We reference the annual AI Index report, which tracks performance across benchmarks and notes when models achieve human-level performance. Other efforts have tried to relate AI performance to broader concerns, but they often lack a unified metric for comparison. We mention the BioAnchors framework, which connects compute usage to the effective length of tasks for transformative AI impacts, and propose using the time horizon where AI outperforms most human experts to measure general AI capabilities. In our work, we empirically assess the relationship between task duration and AI success rates, converting this into a quantitative performance metric. Our methodology is inspired by psychometric testing, particularly item response theory, IRT, which models the link between latent traits and observed test responses. We invert the traditional IRT approach by using task completion time as a proxy for difficulty to predict AI performance. This relates to difficulty estimation techniques in educational testing, where various metrics, including completion time, help gauge task difficulty. Finally, we describe our task suite, which consists of 3 distinct task sets: a subset of HCAST with 97 diverse software tasks ranging from 1 minute to 30 hours, RE-Bench with 7 challenging ML research tasks each lasting 8 hours, and Software Atomic Actions, SWAA, with 66 single-step tasks that take between 1 and 30 seconds. All tasks are automatically scored, and we ensure that they can be reliably completed within a time limit. We confirmed that humans could successfully complete each task at least once, and we organized tasks into families based on similarity to enhance performance correlation while maintaining diversity. Section Summary. In this section, we discuss the evolution of AI capability benchmarks from simple tasks to complex evaluations that assess dynamic problem-solving skills, highlighting various benchmarks like AgentBench and SWE-Bench that measure specific capabilities. We also introduce our methodology inspired by psychometric testing to evaluate AI performance through task completion time, and outline our task suites designed to isolate specific units of work for reliable assessment. Section: HCAST Tasks. In this section, we describe the HCAST tasks, which include 97 challenges from 46 different families, covering areas like cybersecurity, machine learning, software engineering, and general reasoning. These tasks vary in difficulty, with some being simple enough for humans to complete in a few minutes, such as looking up a fact on Wikipedia, while others may take experts several hours, like writing CUDA kernels or debugging PyTorch. Most tasks focus on text-based skills, as modern AI systems excel in these areas, and all tasks can be solved using text editing in a bash shell. Unlike some recent benchmarks that aim to be extremely challenging, we designed HCAST tasks to be realistic and relevant to skills that are economically valuable. We believe that most tasks can be completed by individuals with a few years of professional experience in the relevant field. Each task includes instructions, starter resources, and a scoring system that rates performance from 0 to 1, with higher scores indicating better results. While many tasks yield binary scores of 0 or 1, we also define a success threshold for tasks with continuous scoring to help analyze agent performance. We also introduce the RE Bench Suite, which consists of 7 complex, open-ended machine learning research environments, each expected to take an expert about 8 hours to finish. To address the need for shorter tasks, we created the SWAA Suite, which includes 66 small tasks that represent single-step actions typically performed in software engineering, each taking less than 1 minute. This suite features both multiple choice and completion questions. Unlike other benchmarks that may not relate directly to software engineering, the SWAA tasks reflect actions relevant to both software engineering and our longer tasks. We developed the SWAA tasks without considering AI agent performance beforehand, ensuring that all tasks were created independently of AI attempts. We provide examples of tasks of varying lengths, noting that tasks under 1 minute assess knowledge necessary for professional software engineering but do not require decision-making. Tasks around 1 minute resemble components of economically valuable work, while 10-minute tasks represent the simplest meaningful steps in real software projects. Tasks that can be considered standalone projects typically take about 1 hour, and those that are significantly valuable software projects can take around 8 hours. To establish a performance baseline for AI agents, we measured the performance of over 800 human baseliners on most tasks, totaling 2,529 hours of attempts. Among these, 558 baselines, 286 successful, are from HCAST and RE Bench, while 249, 236 successful, come from the shorter SWAA tasks. Our baseliners are skilled professionals in software engineering, machine learning, and cybersecurity, with most having attended top universities and averaging about 5 years of relevant experience, particularly in software engineering. Section Summary. In this section, we present HCAST, a suite of 97 tasks across various domains like cybersecurity and software engineering, designed to reflect realistic challenges that skilled professionals can solve, with tasks ranging from quick factual lookups to complex coding problems. We also introduce the SWAA Suite, which includes 66 short tasks representing common software engineering actions, and discuss our approach to baselining AI performance against skilled human professionals with an average of 5 years of experience. Section: HCAST Tasks. In this section, we discuss the HCAST tasks. We utilize existing baselines gathered from professionals experienced in software engineering, machine learning, and cybersecurity. These baseliners operate in the same environment as our agents, using Vivaria, with their screens and audio recorded to ensure integrity. They receive bonuses for completing tasks successfully and for doing so faster than their peers. After filtering out unsuccessful attempts and those that violated rules, we are left with 286 successful baselines from around 460 attempts. We calculate task durations using the geometric mean of these successful baselines, while manually estimating durations for tasks without successful baselines. For RE-Bench, we refer to the baselines from the RE Bench paper. Since baseliners aimed for optimal performance, we consider the duration for each of the 6 tasks to be 8 hours. We then use the average score from baseliners who spent between 7 and 9 hours to set the success threshold. In contrast to HCAST and RE Bench, which involved external contractors, SWAA is based on METR employees with relevant expertise using a custom web application for precise timing. The timer for SWAA tasks stops as soon as a user selects a response, as these tasks are designed to be single-step and do not require context acquisition. For decision-based tasks, only one choice is allowed to prevent random guessing, while for fill-in-the-blank tasks, baseliners can attempt multiple times until they get the correct answer or choose to skip. When evaluating AI agent performance on task suites, we reused our previous evaluations for most models. We also included earlier models like GPT 3.5 Turbo Instruct, DaVinci 002, GPT-3, and GPT-2. Detailed information about the models and agents can be found in the appendix. We maintained the same agent scaffolds throughout the evaluation suite, with no specific prompts for tasks, except for SWAA, which used a simple prompt. All agents had the same resources as human baseliners. Most AI models were assessed using a basic agent scaffold called Modular Public, which provides Python and Bash commands along with simple context management. We used a different scaffold for O1 Preview and O1 due to their difficulties with tool use and responding to feedback, as detailed in the appendix. GPT-2 was incompatible with our scaffolding due to its limited context length, so we assigned it a score of 0 for all tasks in Ray Bench and HCAST, which we believe is justified since the more capable DaVinci 002 also scored 0 on this set. Removing these 0 scores for GPT-2 had little impact on our overall results. We conducted 8 runs for each agent task pair and report the average results. As seen in most benchmarks, we observe a significant upward trend over time, with recent models completing about 50% of tasks, while earlier models perform much worse. There is a strong correlation between the tasks that models can complete, with an average correlation of approximately 0.73. We found a negative correlation between the time it takes a human baseliner to finish a task and the average success rate across all models. This decline in success rate as time increases fits well with an exponential model. Notably, the correlation between model success and human completion time is higher than the average correlation among models. We verified this by comparing the completion times of tasks that earlier and later models can handle. As expected, models from before 2023, like GPT-2 and GPT-3, can only complete tasks that require minimal writing, failing all tasks that take longer than 1 minute. In contrast, newer models like Claude 3.5 Sonnet and O1 can tackle tasks that take human baseliners over 4 hours. To provide a clearer metric for AI capability progress, we convert each model's performance on our tasks into estimates of their task completion time horizons. Section Summary. In this section, we describe our methodology for establishing baselines across various tasks, utilizing data from domain professionals and ensuring integrity through monitoring. We also evaluate AI agent performance against these baselines, noting trends in model success rates and their correlation with task completion times, ultimately providing insights into the progress of AI capabilities. Section: From Raw Data to Time Horizon. In this section, we convert the performance of our agents on each task into binary values, indicating success or failure. Many tasks are inherently binary, such as all SWAA tasks and most HCAST tasks. For tasks that are scored continuously, we apply a specific threshold to determine success. For instance, if a task involves minimizing model loss, we classify runs as successful if they achieve a loss below a certain level. This binarization is particularly impactful for challenging tasks like Rebench, where many current models often score 0 since they perform below human levels. We set the task-specific threshold to reflect human performance, using the same target score that human baseliners aim for in HCAST tasks. For Rebench, the threshold is based on the average score of human runs lasting between 7 to 9 hours. Once we have the success rates and time ratings for each task, we draw inspiration from item response theory, IRT. We utilize logistic regression to determine the difficulty level at which an agent has a 50% chance of success. However, unlike traditional IRT, we leverage human baseline data for our difficulty ratings instead of relying solely on agent performance. Specifically, we perform logistic regression using a formula that relates the success probability to the geometric mean time of successful human baselines and learned parameters representing the 50% horizon time. We also calculate excess success rates, which measure how much better or worse an AI agent performs compared to expectations based on task length and the model's capabilities. The average correlation of these excess success rates across all tasks is 0.40, indicating a moderate correlation in performance when accounting for task length. Next, we analyze the relationship between model horizon length and release date. We plot the time horizons of each model against their release dates and find that the time horizon has doubled approximately every 212 days, with a confidence interval of 171 to 249 days. Although individual model horizon lengths have wide error bars, these errors are correlated across models due to varying task difficulties. Thus, we have more confidence in the overall trend of time horizon growth than in the specific horizon of any single model. Over the period from 2019 to early 2025, we observe a significant increase in horizon lengths. Base models like GPT-3 can handle simple tasks but struggle with anything requiring more than a minute. In contrast, chat models like GPT-4 and Claude 3 Opus can frequently complete easier HCAST tasks, achieving time horizons in the 5 to 30-minute range. Notably, the trend in 2024 and early 2025 appears to be accelerating, with models like o1 and Claude 3.7 Sonnet performing above the long-term trend. To assess the impact of our choice of a 50% success rate, we also calculate the time horizon for tasks where AI agents achieve an 80% success rate. The doubling time for the 80% horizon is similar to that of the 50% horizon, at around 213 days. However, there is a significant difference between the 50% and 80% time horizons for models, with Claude 3.7 Sonnet having the longest 80% horizon at about 15 minutes, compared to its 50% horizon of 59 minutes. This gap indicates that even models that occasionally succeed on challenging tasks struggle to consistently perform on tasks of moderate length. Section Summary. In this section, we describe our method for converting agent performance on tasks into binary success rates, using task-specific thresholds based on human performance to binarize scores. We also analyze the relationship between model time horizons and release dates, finding that time horizons have doubled approximately every 212 days, while noting a significant gap between 50% and 80% success rates for AI agents on tasks. Section: Qualitative Analysis. In this section, we analyze the qualitative aspects of our findings. To understand the trend of improved model performance, we review transcripts from tasks where earlier models, like GPT-4, performed significantly worse than current models. We categorized tasks based on the expertise needed and found that current models excel in areas such as machine learning training, reverse engineering software, and cybersecurity challenges. We also observed substantial improvements in tasks requiring awareness of the AI agent's limitations and strategies to counter opponents. This led us to identify 5 task families for further examination. For each task family, we had contractors manually review all model runs and identify reasons for performance improvements and limitations. We discovered that models have enhanced their tool usage, adapted better to mistakes, and improved in logical reasoning and code generation tasks. However, AI agents still struggle in complex environments lacking clear feedback or requiring proactive information gathering. We provide examples of these improvements and limitations in the appendix. To further understand the differences in failures between current and older AI agents, we sampled unsuccessful runs from our GPT-4 and o1 agents, categorizing failures into 3 types: poor planning and tool choice, incorrect reasoning, and premature task abandonment. We found that over a third of GPT-4 failures were due to repeating failed actions, while only 2 out of 32 failures in o1 were attributed to this, supporting our claim of improved adaptability in newer models. Interestingly, half of the o1 failures were due to premature abandonment, compared to a quarter for GPT-4, which may indicate that o1 faced more challenging tasks or had unique characteristics. To assess the broader applicability of our results, we conducted 4 supplementary experiments. First, we checked if the trends from 2023 to 2025 align with data from 2019, and they do. Second, we labeled tasks based on 16 messiness factors that reflect real-world task differences and their relevance to AI performance. Third, we calculated the time horizons for AI agents on verified tasks, noting a similar exponential trend but with a shorter doubling time, likely due to underestimations in easier tasks. Finally, we compared the completion times of our contracted human baseliners with repository maintainers, finding that our contractors took longer, and AI performance was more aligned with contractor times than maintainer times. As part of our exploratory work, we measured the time horizon of 9 advanced models released in 2023 and 2024, observing that the time horizon doubles approximately every 6 months. However, with limited data from 2023 models, our error margins were wide. When focusing solely on 2024 models, we noted a different trend with a shorter doubling time. To improve our data, we developed the Software Atomic Actions (SWAA) suite, which allowed us to measure additional models and confirm that the 2023 to 2025 trend aligns well with longer-term trends. The overall measured doubling time from 2019 to 2025 was about 212 days, closely matching the 191-day trend from non-SWAA tasks. Section Summary. In this section, we analyze the performance improvements of current AI models over earlier ones, particularly in tasks requiring specialized expertise, and identify key areas of enhancement such as tool use and adaptability to mistakes. We also categorize failures in AI agents, noting significant differences in error types between models, and validate our findings through supplementary experiments that confirm trends in AI performance over time. Section: Messiness Factors. In this section, we discuss the factors contributing to messiness in real-world intellectual tasks, which often include unclear specifications, feedback loops, and the need for real-time coordination among various work streams. We noticed that agents tend to struggle more with tasks that have these messy details. To explore this, we evaluated HCAST and RE bench tasks based on 16 characteristics that reflect how real-world tasks can be more challenging and relevant to AI performance. Examples of these characteristics include whether the task is novel, limited by resources, requires real-time coordination, or is derived from real-world scenarios. We assigned a messiness score to each task, ranging from 0 to 16, with an average score of 3.2 for HCAST and RE bench tasks, and none exceeding 8. In contrast, a task like writing a good research paper would score between 9 and 15. Our findings indicate that AI agents perform worse on messier tasks than expected based solely on task length, with an increase in messiness leading to an approximate 8.1% decrease in success rates. However, performance trends over time appear similar for both messier and less messy tasks. Next, we applied our methodology to SWE Bench Verified, a benchmark for evaluating language models in software engineering. The tasks in this dataset are sourced from large open-source projects and are designed to be well-defined and automatically checkable. We observed an exponential growth trend in model performance from late 2023 to 2024, with SWE Bench Verified showing a shorter doubling time compared to our other benchmarks. We also found that our time estimates for SWE bench tasks may underestimate the time required for less capable models. Additionally, we conducted internal experiments using GPT-4o, Claude 3.5 Sonnet, and o1 on real issues from an internal METR repository. We found that our contract baseliners took significantly longer to resolve these issues compared to repository maintainers, suggesting that our time estimates may better reflect the work of lower context humans. Finally, when predicting when AI systems will be able to autonomously generate significant economic value or perform potentially harmful actions, we chose a 1-month horizon for our analysis. This timeframe aligns with the period when new employees typically start contributing economically and allows for a fair comparison with human capabilities. We aim to forecast when ICE will reach a 50% reliability threshold for tasks of this length, as achieving this could have transformative implications for society. Section Summary. In this section, we analyze how messiness factors in tasks, such as unclear criteria and real-time coordination, impact AI agent performance, finding that messier tasks lead to lower success rates. We also explore performance trends across different benchmarks, noting that while AI agents improve over time, the time taken to complete tasks varies significantly between AI and human workers, which informs our predictions about AI's future capabilities. Section: Sensitivity Analysis. In this section, we conduct a sensitivity analysis. We recognize that while extrapolation is never perfect, predicting how long it will take for AI to reach certain milestones is highly sensitive to changes in the rate at which capabilities double, rather than to fixed factors in the time frame. For instance, if we take a simple prediction based on an AI's time horizon of 39 minutes and a past doubling time of 218 days, we estimate that ICE will achieve a 1-month time horizon, equivalent to about 8 doublings, around 4.8 years after the release of the AI. If the doubling time were to double, this would push the 1-month milestone back by another 4.8 years. However, if we simply reduce the time horizon by half, it would only delay the milestone by 0.6 years. We present a figure that illustrates our sensitivity analysis, which accounts for various sources of uncertainty. The term bootstrap tasks reflects our limited number of tasks and the varying difficulty of tasks that take the same amount of human time. Bootstrap runs comes from the limited number of runs we conducted, and the combination of these two factors is shown as a confidence region in the figure. Bootstrap models indicates the limited number of models we have in our dataset. The weighting regularization aspect refers to our methodological choices, which include 10 combinations of hyperparameters with and without task diversity weighting, and a logistic regression regularization parameter ranging from 0.01 to 0.2. IID baseline noise involves multiplying each task duration by a random factor based on the observed distribution of baseline times. We combine these elements to estimate the overall uncertainty in our past trends and apply the same approach to the trends for 2024-2025, although we have less confidence in this latter trend due to only having 6 models in that timeframe. Our analysis suggests that it is unlikely for the growth rate of the time horizon for our tasks to be slower than 1 doubling every 8 months, leading to a relatively small uncertainty in the predicted date for achieving a 1-month AI, with an 80% confidence interval width of about 2 years and a central estimate around late 2029. The majority of this uncertainty stems from bootstrapping over our task distribution and runs, reflecting our limited dataset and the variance in task difficulty. If future progress aligns with the 2024-2025 trend, we could see a 1-month AI emerge sooner, with a 50% chance of it happening in 2027 or early 2028. We also acknowledge that systematic biases and different methodologies could significantly affect our forecasts, which we discuss in the appendix. Furthermore, we recognize that predicting the future is inherently challenging, and actual forecasts will likely have greater errors than our simple extrapolations. We also address the difficulties in extrapolation. Much of our uncertainty about the future arises from 2 main factors: A, the applicability of our tasks to real-world scenarios, which we partially discuss in another section, and B, potential future changes in the growth rate of the time horizon. We note that the tasks we use to evaluate AI capabilities differ systematically from real-world tasks. These differences may mean that the trends we observe in our tasks do not apply to real-world situations. For example, all our tasks are automatically scored, which limits the format of solutions and reduces the need for subjective judgments. Additionally, none of our tasks require interaction with other agents, which could complicate task difficulty through strategic decision-making and real-time coordination. Our tasks also do not impose strict resource constraints, and they are generally forgiving of mistakes, unlike many real-world tasks where a single error can have significant consequences. Lastly, our tasks typically occur in static environments, while real-world tasks often involve changing conditions. We attempted to assess how these differences might impact AI performance by including these characteristics as messiness factors in our analysis. We found that while performance on messier tasks was lower, the trends remained similar to those on less messy tasks. Nevertheless, these systematic differences raise questions about whether the rapid performance improvements we observe will translate to real-world tasks. Regardless of whether our trends apply to real tasks, we believe our findings are important. If our results do not generalize, benchmarks like HCAST and SWE Bench Verified may not be adequate for predicting AI capabilities in real-world scenarios, suggesting a need for more realistic benchmarks. Conversely, if our results do generalize, our trend suggests that ICE capable of automating a month of human software development could emerge before 2032. Section Summary. In this section, we analyze the sensitivity of AI horizon length forecasts to changes in doubling rates, finding that a doubling time increase significantly delays predictions compared to constant factors in horizon length. We also discuss the limitations of our task benchmarks, which may not accurately reflect real-world tasks, potentially affecting the generalizability of our results and the reliability of our forecasts for AI capabilities. Section: Future changes in time horizon trends. In this section, we discuss 3 additional factors that could significantly impact the growth rate of time horizons: agency training, compute scaling, and automation of AI research and development. For agency training, we believe that the growth in time horizons since 2024 may be quicker than the long-term trend. This could be due to researchers making models more agentic, meaning they can perform multiple actions to complete tasks using outcome-based reinforcement learning. We expect research in this area to continue, and future agency training might be more efficient than previous methods. However, the growth could also be a temporary boost from easily achievable improvements, which would slow down once those gains are fully realized. Overall, we think agency training is likely to enhance the growth rate compared to the trend from 2019 to 2024. Regarding compute scaling, we note that the compute power used to train leading language models has increased dramatically, by at least 10,000 times since the release of GPT-2, with training compute doubling every 6 to 10 months. Recently, models have also started using more compute during inference. It's uncertain if we can significantly increase compute capacity in the next 5 years. However, algorithmic advancements can help reduce compute needs for a given performance level. We believe that while compute scaling limitations may slow the growth of AI agent time horizons, increased investment in algorithmic improvements will help offset this. On the topic of automation in AI research and development, we recognize that the main resources for AI R&D are compute and researcher time. If future AI systems can replace human researchers or enhance training efficiency, we expect the pace of AI progress to accelerate. We anticipate significant automation in AI R&D once the time horizon of frontier AI reaches several hours, which would shorten the time until we achieve 1-month horizon AI. When it comes to measuring and interpreting time horizons, we find that while it is a useful measure of AI capability, it requires a large dataset annotated with human time. Time horizons are always relative to specific tasks and the context and skill levels of human baseliners. We observe that in real companies, junior software engineers often need weeks of onboarding before they can contribute effectively. The human baseliners we use to determine task lengths may have less context than average employees, which could lead to longer measured task lengths. Our tasks are designed to minimize context requirements, but our internal processes were not, resulting in longer completion times. Conversely, highly skilled baseliners can complete tasks much faster than average employees, which may reduce our measured task lengths. We also note that the success rate of AI agents is not solely predicted by human completion times, indicating that other factors influence task difficulty. We expect time horizons to vary across different domains of intellectual labor, such as research mathematics or law. Measuring extreme time horizons accurately requires many tasks that humans complete in a specific time frame, with the AI achieving a certain success rate. This presents challenges, as constructing datasets of difficult tasks with long human baseline runs can be impractical, especially when success criteria are complex. Additionally, Measuring time horizons at very high success levels requires large datasets with minimal noise, covering the full range of tasks. We conclude that an artificial general intelligence, AGI, with the ability to complete all tasks that expert humans can, with a certain success rate, would have an infinite time horizon. This does not imply unlimited capability but rather the ability to handle tasks that take humans a long time. If such AGI systems are developed, we expect the long-term trend in time horizons to grow faster than exponential, reaching a limit at the point of AGI deployment. Lastly, while it is theoretically possible to measure the time horizon of humans or groups, there are significant theoretical and practical challenges involved, which we discuss further in the appendix. Section Summary. In this section, we explore factors that could influence the growth rate of AI time horizons, including agency training, compute scaling, and automation of AI research and development. We believe that agency training may accelerate growth beyond past trends, while compute scaling could slow it down, and automation could significantly enhance AI progress as capabilities improve. Section: Limitations and Future Work. In this section, we identify several areas for improvement in our work. First, we recognize the need for more models with better elicitation. We have found that effectively eliciting models can significantly enhance their performance. Our efforts in this area have been limited, so while our results provide a reasonable lower bound, some models may perform better than we have shown. We dedicated the most effort to eliciting 2 specific models, each requiring about 2 to 3 weeks of development, while other models used similar frameworks with only minor adjustments. Future work could focus on fully exploring the capabilities of advanced models. Next, we see the importance of more rigorous human baselining. Our estimates of human performance on tasks may be unreliable due to a small sample size and potential biases. We only selected successful task completions and encouraged participants to abandon tasks they might not finish in a reasonable time. Additionally, the skills of our participants varied widely, which could affect the results. We noticed that some individuals gave up even when they could have succeeded, and it's unclear how this impacts the distribution of success times. Future research could improve our results by refining the selection of human baseliners or examining how sensitive our findings are to the methods used for human baselining. We also believe that our task distribution may not accurately reflect the types of economically valuable work or relevant risk model tasks. We discussed some of these differences, but many remain unexplored. For instance, our tasks do not require mouse usage or collaboration with other people, which is common in real software engineering or machine learning research. Many real-world tasks demand high reliability, which is underrepresented in our dataset due to measurement challenges. Our focus has been primarily on software engineering and ML research, so future work could investigate AI capabilities in other fields. Furthermore, we note that our frameworks utilized limited inference time computation. Assuming a human expert's hourly rate, over 80% of successful runs cost less than 10% of what it would take for a human to complete the same task. This suggests that there is significant potential to enhance performance through better use of inference time computation while remaining cost-effective compared to human experts. Previous studies have shown that techniques like best of K can improve performance on some tasks, indicating that optimizing inference time computation could lead to better results. In summary, we introduced a straightforward metric for assessing AI capabilities: the task completion time horizon, which compares AI performance to the time human experts typically need for tasks. We created a dataset of 66 shorter tasks, combined it with data from other sources, and conducted 236 human runs to estimate task difficulty. We benchmarked 11 advanced AI models released between 2019 and 2025, calculating their time horizons and observing an exponential growth in the 50% task completion time from 2019 to 2025, with a doubling time of about 7 months. The 80% time horizon showed a similar trend but was roughly 5 times shorter. Our qualitative analysis highlighted factors contributing to this progress and noted limitations in current systems, especially regarding less structured tasks. We replicated our methods on another benchmark and found a similar exponential trend, but differences between benchmarks and real-world tasks may limit generalizability. Finally, we extrapolated our findings to predict that if current trends continue, AI capable of completing one-month-long software tasks could be released between late 2028 and early 2031.